Welcome to what will be pre-lecture 12 for our lecture that will be on Friday, September 16th. We're going to be continuing in chapter 4 here, talking about molecular geometry. So, just so you know, by the end of the class you should be able to explain these concepts and do these things. So, define electronegativity, how it relates to atoms, how we know about it, and its trend on the periodic table. Should be able to determine partial charges on molecules, should be able to determine the number of bonding and non-bonding domains on a central atom. You should be able to translate that number into a geometrical structure. Okay. So prior to this, we've talked about formal charge and how we calculate that. And typically when we've been doing this, we've been looking for either 0, +1, or -1, which is a full formal charge, right? So we know that in reality they aren't full positives or full negatives, but something close to it. In reality, many of our atoms actually possess partial positives or partial negatives. We often indicate that with this Greek symbol, lowercase delta. So this would be a partial positive here and a partial negative there. And the reason we have partial differences are based on differences in a property called electronegativity between atoms. And so if we define that, electronegativity is the relative ability of an atom to draw electrons in a bond towards itself. And so hopefully this makes some amount of sense. Basically, the smaller our molecule is, or smaller our atom is, the more the electrons are going to feel the pull of the protons that reside in our nucleus, and that is going to make things more electronegative. So for example, fluorine is going to be our most electronegative atom that we're going to deal with. And then cesium, down at the lower left corner of the periodic table, is going to be the least electronegative. Okay? And so if we want to draw differences in partial charges, for example, for HCl here, we can represent those differences in electronegativity where we have a partially positive side of the molecule, which would be our hydrogen here, partially negative side of the molecule that would be our chloride. And that is because this chlorine is going to be more electronegative than this hydrogen. And so you might say, how do we know that? Here is a chart that gives you the relative values of electronegativity for atoms on the periodic table. We'll say that electronegativity is not something that is a value that has units. It's all relative and it's all unitless. Generally speaking here, things on the left side of the periodic table have very low electronegativities. Things on the right side have pretty high electronegativities. And so another way we could represent that, we mainly care about the main group elements. So again, pretty low electronegativities here with our left side of the periodic table, and then as we go right and further up the periodic table, our electronegativities go up and up. This chart shows our noble gases. Those tend not to react, so something like neon, despite it technically having a higher electronegativity than fluorine, because neon doesn't actually react with anything, we functionally just ignore it. Okay? All right, so that's partial charges. We're going to change gears just a little bit here and talk about molecular shape. And so something you've probably figured out by this point is that most molecules exist in 3 dimensions. Obviously, we are 3-dimensional ourselves, and we are ultimately made of atoms, so it would make sense that they too are 3-dimensional. And their geometry can have huge effects on the type of reactivity they're able to perform. And so it's important for us now to be able to describe a molecule's geometry accurately from its Lewis structure. And so this is most commonly done using a theory called valence shell electron pair repulsion theory, or VESPER model, we could also say. And in this model, our valence electrons exist as bonding domains, aka bonds of some sort, or non-bonding domains, which we would call lone pairs. And the number of bonding and non-bonding groups around a central atom will ultimately determine its geometry. Okay? And so the big assumption that Vesper makes here, and it's generally a pretty good one, is that the arranging of these domains in space, or these domains are arranged in space so that they are as far away from each other as possible. That allows for the lowest energy conformation, or you could also think of that as being the happiest molecule. Okay? So here's a moment for you to think. What are the Lewis structures for beryllium dihydride, BeH2, boron trihydride, so BH3, and then CH4, which we would call methane. And then you could think, what are the angles between those bonds? So if you want to pause the video, you can draw those out. I'm going to go ahead and talk about them now. So hopefully this is what you got for Lewis structures here. Your beryllium and your boron are probably ones you've already drawn at some point. And this CH4 is probably one you've drawn, although we're adding in this new element here. And so you'll notice that we have two straight lines. We also have what we would call a wedge line. So when we draw in a wedge here, what that means is that hydrogen is actually coming out of the plane of our screen towards us. Then we also have a dash, so this back hydrogen is a dash. That dash means that our hydrogen is going behind the screen. And so this is how we represent things in 3 dimensions when drawing molecular structures. Okay? If we think about how these would exist in 3D space another way, we can also talk about the angles here, where if we treat our hydrogens just as spheres, if we have 2 spheres, then our angle between them would be 180 degrees. If we have 3, then the angle here is 120 degrees. And these happen to all be in the same plane. Finally, once we break into 3 dimensions here, we get 4 domains. We would say our bond angles then 109.5 degrees. And what you're doing in lab this week is more practice in reflecting these realities, basically, for our different types of molecules. Okay? If we were to name the geometries here, we would call this, excuse me, sorry. We'd call this beryllium compound linear. We would call this BH3 molecule trigonal planar, so the trig meaning 3, right? 3 sides, and planar meaning flat. And then we call something with 4 groups around it with this 3D structure tetrahedral. And that is a word that hopefully you've heard before. If not, you're going to be hearing it a lot in class and through the next couple weeks. Okay. So this is what things look like with different numbers of bonding groups. And so if we have 2 bonding groups, our bond angle should be 180, and we would call that geometry linear. Trigonal planar, same example here, except with fluorines instead of hydrogens. We end up with that 120 degree bond angle in a flat molecule. If we have 4, we end up in a tetrahedral. So in 3D space, that looks kind of like this 4-sided prism, right? Where we have 4 sides forming a pyramid, essentially. Once we get beyond that, so say we have 5 bonding groups, something like PF5, and this would, I believe, have a minus charge as well. We would want to have a trigonal bipyramid. And so in this case, we now have 3, so similar to our trigonal planar, but instead of things being empty above and below our plane, we have them filled. And so we have 2 pyramids stacked on top of each other, thus the bipyramid. Okay? And then finally, if we have 6 bonding groups, then we have 4 around the belt of our central atom, so this is SF6, and then we have an F above and below, so we ended up with a 4-sided pyramid, and they're stacked upon each other. We call this an octahedral because when we draw it this way, it has 8 faces. Okay, so you could think of this like an 8-sided die or something. And then the bond angles there are all 90 degrees. Okay. So hopefully that was helpful. We're going to talk about what happens if we have lone pairs on our central atom in class, but hopefully that was a good introduction. And if you have any questions, of course, please feel free to let me know. Otherwise, have a good day.